Thank you for all joining this webinar hosted today by the manufacturer and Stratasys. My name is Callum Bentley. I'm the editor of the Manufacturer magazine, and I'm joined today by Frank Schauflin from Stratasys. At the Manufacturer, over the past couple of years, we've been focusing a lot of our editorial direction on the benefits of additive manufacturing and 3D printing. And we believe this is a fundamental part of the future of manufacturing, not only here in the UK, but across the globe as well. As part of this approach at the Manufacturer, mainly over the past 6 months or so, we've kicked off our latest initiatives, and those are what we call our thought leadership networks. So what I'm going to do, I'm just going to share my screen with you now in order to show you what these actually look like. So this is an example here of one that we've started for manufacturing services. We also have them for automation as well. And what these are, they're basically digital social networks where manufacturers can meet online to share thought leadership, best practice, or simply ask questions of other members on particular topics. We've already launched 2 of these thought leadership networks in the past 6 months. As I mentioned, this one here, which is manufacturing services, and another one which is in automation. However, our latest thought leadership network which we're just ready to launch now, is the Additive Manufacturing Thought Leadership Network, which is a large part of why we're here today as well. So the aim behind the Thought Leadership Network is to dispel myths currently associated with additive manufacturing and 3D printing, to show how this technology is no longer just about printing plastic iPhone cases, or it's not about the gimmicks anymore. It's instead we're trying to highlight through knowledge sharing how 3D printing and additive manufacturing can speed up the time to get products to market, reduce production costs, dramatically shift the idea of rapid prototyping, and I guess even change the way we design and manufacture components for our customers as well. So today you will hear directly from industry expert Frank Schauflin from Stratasys, who will explain the transformational benefits of 3D printing solutions for injection molding, beads and fixtures, end-of-arm tools and production parts. You'll learn how additive manufacturing enables businesses to create custom end-of-arm tools ideally shaped for each job and fitted with the perfect array of features to boost production efficiency as well. I'll just make a note as well. You should see in your webinar box over on the right the ability to ask questions. So there's a little question box on the right-hand side panel on your screen. When you click that, you'll be able to type your questions, which will come through to us. So please, as the webinar is going on, please feel free to use this to ask any questions that pop up as we proceed, and we'll endeavour to answer as many of those as we can at the end. So thank you everyone for joining us today for the webinar with Stratasys, and please do enjoy it, and I do hope you find it interesting. I will now hand over to Frank from Stratasys.
All right, now you should see my screen. Good afternoon, everybody. My name is Frank Schauflin. I'm with Stratasys. Let me just quickly introduce myself. I am the senior sales support and application manager at Stratasys. My duty is to not so much focus on our products, but more on what the industry is doing with it. So it's really more about the application of basically the parts which are produced with 3D printers or additive manufacturing devices. So I'm with Stratasys since almost 20 years now, and I started in the industry in 1988. So I consider myself as being sort of a dinosaurus in everything which is in layers. Today I'd like to present or introduce to you some examples of what can be done with all these 3D printed parts. And it's not really talking so much about potentials or opportunities, but it's more like a state-of-the-art status of what is currently done in industry. So it is really the present and not so much the future. Now I'm going to talk about how to reduce the tooling cost by up to 95%, how to reduce lead time significantly, how to increase performance of parts by combining conventional and additive manufactured components, and also how to manufacture finally production parts quickly using additive manufacturing, also known as 3D printing. So I've already mentioned right now 2 terms, 3D printing and additive manufacturing. And here is how Stratasys differentiates between both. So on the left side of the screen we see concept modeling and functional prototyping, which is the area we call 3D printing and or prototyping. On the right side, you see the two icons for the manufacturing tools and aids and the production parts, and this is what we consider or call additive manufacturing. And this is a trend you can actually even see in the industry, where the, let's say, creative product design and optimization is more residing in the 3D printing area, and the additive manufacturing area is where basically the technology hits the workshop. Today, I would like to focus on the right side, which is manufacturing tools and aids and the production parts. Now let's have a quick look on how Stratasys defines or explains both. Let's have a quick look to the manufacturing tools and aids. Here we talk about jigs and fixtures and manufacturing aids in order to hold pieces or store them or transport them. We talk about end-of-arm tools, which is basically everything which is attached to the arm of a robot. And we will talk about, or I will talk about, a very specific application, which is the production of injection molds in plastic. And the other part of the world, which is basically the right side of additive manufacturing, is to produce the real parts, which are then used for something. Parts which are produced in either small series or have a very high complexity, which is very difficult to make otherwise, or it is also talking about the increasing or the mass customization, which is gaining more and more increased importance in the market. Before starting with the applications, let me just quickly talk about the technologies I will mention. So on the left side, you see the so-called polyjet technology, which is a technology very similar to your inkjet printer, but instead of printing droplets of ink, it is printing droplets of a photopolymer, which then is cured by ultraviolet light. And on the right side, you see the FDM technology, stands for fused deposition modeling, where we are extruding fused thermoplastic materials by a little nozzle. So on the left side, it's basically a printer, and on the right side, it's more comparable to a plotter. The major difference is not so much the technology, but the possibilities and the materials you have with it. So with the polyjet technology, while printing little tiny droplets, you can print very fine feature details, but on the other hand, as like with an inkjet printer, you can produce a very high material versatility. Imagine you have different colors on your inkjet printer, different colors cartridges. You can start mixing these colors and really reproduce a large number of colors. We can do the same with materials, reproducing not only a large variety of colors, but also a large variety of material properties. Where on the right side with the FDM technology, we're using real industrial-grade thermoplastic materials with the advantage to be known in the industry, and it's the same identical materials which are used for the washing machine, the car you're driving, but even on the airplane you took for the last vacation. So let's come to the applications. We're going to talk about, as mentioned before, we're going to talk about 3 applications which are tools and devices for production, and the 4th application is really the production parts. So let's have a look to the jigs and fixtures. Now the jigs and fixtures are typically used to position, hold, or protect parts during the manufacturing process. And using additive manufacturing for jigs and fixtures, it's basically used for quickly matching complex parts or reducing the need of drawings, paper drawings, basically really making the step to the digital manufacturing. And of course, it gives the possibility to create fixtures with very high complex shapes. Where do these jigs and fixtures, or let's say, where does additive manufacturing fit the jigs and fixtures manufacturing? It's basically allowing high complexity design of these jigs and fixtures. It is an important point is the reduction of the need to assemble these fixtures. And of course, another best fit is if you are dealing with frequent changes. Another very important point is if you are dealing with different loads and temperatures and exposure to chemicals. This is where some technologies might be better suited or better fit the application than others, especially the industrial production grade thermoplastics. A best fit of additively manufactured jigs and fixtures is if you have parts which are, well, I would say 1 meter is already quite a bit. I would probably say jigs and fixtures somewhere up to 600 millimeters, that's easily feasible. Up to 1 meter, it is absolutely feasible, although I don't know if it always makes sense. And then, of course, watch out for the tolerances, that we can produce parts with a tolerance of plus minus more or less like 1/10 of a millimeter. Now, what are the benefits in producing jigs and fixtures with additive manufacturing? It is mainly to improve the efficiency, but especially also to improve the ergonomical aspects of my jigs and fixtures. And here you see 2 examples. Let's start with the bottom example. That's an example of a fixture to apply the M3 emblem on the back of the BMW truck. And here, this fixture, as you can see, it really looks like the steering wheel of an airplane. This is to allow the worker to better hold these fixtures and without getting tired too early, and in consequence improving the quality of the application of that emblem. On the top you see another example of a fixture which is used to mount the airbag sensor underneath the front bumper of a car. Again, a BMW example. And you see that this fixture is rather complex because it allows one worker to take that fixture, grab the sensor, put it underneath the bumper, and have the second hand available for the power tool to mount the fixture. Without this fixture, it would be required to have a second worker holding that power tool while the first one is holding and positioning the sensor underneath the bumper. And you can also see on this example that there are certain mechanisms, a few mechanisms like magnets, like mechanics incorporated in this fixture in order to allow the worker to grab the sensor with one hand. There is a little red release button, hard to see on the back of the fixture, but this is the only button which is used to grab and to release the sensor. Then, of course, it's also the fixtures are also used to reduce the cycle time and reduce the labor effort which is required for assembly. And another very important point is to reduce the documentation of these fixtures. It means, in other words, that if you're able to reproduce this fixture at any given time, you can pretty much scrap the fixture, scrap the documentation if required, if you can guarantee that you can reprint this fixture at any given time with the same geometry and the same properties. Let's step to the next one, the end-of-arm tools. That's basically everything which is attached to a robot. And here you see very, very simple examples, but these examples are actually simple enough to ask the question if I really need aluminum in this case. So the end-of-arm tools are basically used to hold, move, and transport products. And the additive manufacturing is good for increasing the throughput, increasing the speed, increasing the flexibility. It's basically the response if I have a product change and I need to change all my manufacturing and my workflow and my devices. It is relatively easy to reprint an end-of-arm tool. Something which is missing here is actually the possibility to make lightweight components, which I think we're going to see on the following, on the following slide. So the best fits are all the cases where I need high complexity equipment, where I might actually need organic shapes in order to reduce the weight. So in automation and robotics, I have to reduce somehow the weight in order to increase the payload I can transport. So weight reduction in robotics is relatively frequent, and it's a high demand currently. And something I've already mentioned before is the flexibility and the fast reaction to product changes. The benefits of using additive manufacturing for end-of-arm tools is the reduction of design constraints. Since I am manufacturing the parts in layers, I can pretty much print whatever I want, whatever geometry I want. So no matter how complex the parts are, I can print it. I can optimize my parts for functionality. This means that I can adapt the geometry of my gripper to the geometry of my product. And here we see an example of a robot gripper which is using vacuum to hold a piece of metal while it is processed. First it's water jet cutting, and then it's smoothing the corners. So this is a very simple example, but now imagine the toy industry and the robot gripper you need to pick up the Mickey Mouse. So this robot gripper might probably be very, very complex because there is no way to grip that Mickey Mouse figurine. And in this specific case, robot grippers which are following the shape of the product they have to pick up might come in very suitable. Of course, printing a robot gripper might be significantly less expensive than milling such a robot gripper out of aluminum. Let's step to the next application, which is injection molding. So if I say injection molding, it is basically printing the injection mold out of plastic. And in this specific case, other than in the previous examples, this mold is printed with the photopolymer. And here we are manufacturing, instead of the product itself, we make the cavity where then we can inject the final material, which is used for production later. And this is really used for design verification and especially mechanical testing of my final product, like lifetime testing or testing of the resistance in different environments. So what is it good for, really? If we quickly look at the workflow or the design cycle of an injection molding part, we can see on the very left that we start with a CAD system, the part is designed, then probably somebody has the idea to produce a prototype, and this is typically for concept or simulation. So basically we talk about a rapid prototype. But then at a certain point I need a second prototype in order to test the function with the real material and with the full range of tests I can make. So I need the original material, first thing. And this is something which very often is very hard to simulate. Sometimes it's feasible, but on the other hand, I need also a verification of my final production process. So if I make a real prototype for testing, I need not only the real material, but I also need the real manufacturing method. And this is where the printed molds come into the game. So the best fits of these molds are for thermoplastic materials with moderate temperatures. What is a moderate temperature? Something which is somewhere around 250 degrees centigrade. Moderate pressures. Well, the moderate pressures, I don't even have a rough number for you because this pretty much depends on the geometry of the part and the geometry of the mold. I think it is relatively obvious that I should have a material with a good flowability and, of course, for using standard industrial plastics. And, of course, I should use these plastic molds or the photopolymer molds with relatively moderate clamping forces. If I say moderate clamping forces, I'm talking about somewhere between 50 and 100, probably even 150 tons. You can certainly imagine that the quantities of parts you can inject in a photopolymer mold might be reduced. So here we're talking about 5 to 100 parts, although I would like to point your attention to the graph on the right side, where on the very front you see molds manufactured with a photopolymer by the polyjet technology. And you see on the left side the graph of the number of shots you can make in such molds. And on the bottom you see 4 classes of materials. So if we use polypropylene, for example, well, you can actually even easily exceed the 100 shots, even the 1,000 shots. I mean, it's a really easy material. But on the other hand, if we go to the extreme of polyphenol sulfone or even PEEK, for example, you can certainly imagine that the number of shots is significantly limited, and it might actually get down to 0. So the truth of the quantities of parts you can inject in such a photopolymer mold is really depending on the material, but it's also depending on geometries and draft angles and the depth of the cavities, for example. And last but not least, we suggest parts somewhere with a volume somewhere lower than 150 cubic centimeters. I would even go a little lower, although even larger parts have been done. But then, of course, again, reducing the number of shots. Let's have a quick look to the benefits of the injection molds. Of course, it's to reduce lead time, reduce the cost saving, but also to increase the speed and reduce the time you need to verify everything, because all of a sudden you might have a mold making in-house, which otherwise you would have to outsource. So having the possibility to make the design iterations in-house becomes more and more an issue and an important argument. So far about the manufacturing aids and tools and devices. Last but not least, let's talk about the production parts. And here we talk really about additive manufacturing for the final product. So what is it good for? Where is it used? It's mainly used in pilot production before you actually start the production and you do some alpha or beta testing. Or it's used also while you're waiting for the tools and devices for the final production. But sometimes it's even used for full-scale manufacturing. And here it really depends on how many parts you need. What is that final production? And it's certainly not talking about millions of parts. But if we talk about a series, which might be 1,000, 2,000, 5,000 parts, additive manufacturing might start being a serious, significant option. Then, of course, we're talking about the end-of-life production when the tools are no longer available, or repairing of tools might not make sense anymore because the production life, the product life is ended anyway. And last but not least, it's really to produce spare parts for repairs, for example. If you have a decentralized maintenance facility, then you might actually, instead of having local spare parts inventories, you might start considering having a local additive manufacturing device which can produce spare parts on demand. No, I am not talking about the wing of an airplane. Yes, I'm certainly talking about the closing latch of a fridge. So it really depends on what these parts are. The best fits of production parts manufactured with additive manufacturing is, and here I slightly disagree with the slide, it is not 1 to 1,000. I have seen people which are making 5,000 parts and more over the years. So it really depends on the cost of inventory, for example. Now, mass customization is something I've already mentioned, and here the number of parts can increase significantly, and we can easily talk about 10,000. If they're all different, well, then it starts really making sense. frequent revisions of parts, if you have frequent changes with a very short product lifetime, like in aerospace where you have frequent changes, well, that's another area where additive manufacturing starts being used, but not only in airplanes. Imagine ambulances with different legal requirements. Well, there are many and frequent changes there as well. And that's another example where additive manufacturing is used for production. Then, of course, finally, the complex design, which I've already mentioned before. The benefits of additive manufacturing in production are, again, the lead time, just-in-time, digital inventory. Well, the digital inventory is something which starts being more and more important, especially if we start considering the databases of products in the internet, where you don't really have inventory of physical parts anymore, but you might have libraries of geometries you can download, and then you can manufacture somehow automated. The optimization for performance, this is basically something which could pretty much fill an entire webinar, because here we talk about not only topological optimization of geometries, but also about internal structure of lightweight parts. Since we are not limited in the geometry, we can pretty much print everything. Then, of course, cost reduction and flexibility in the typical suspects are included as well. And last but not least, let me just quickly give you an outlook of advanced manufacturing. That something I've already mentioned in the previous slide. It is really changing the way we think about manufacturing, changing the possibilities we have in manufacturing, and this is something which starts coming up in the industry right now, where people realize the freedom they have in using additive manufacturing technologies for their products. And this is basically all I have to say about the subject, so I'd like to thank you for listening, and if there are any questions, please feel free. Thank you.
Thanks, Frank. That was really insightful, actually. Great look at 3D printing and additive manufacturing, and a lot of those I'd never really thought about the applications that you've got there as well. Particularly looking at the end of arm tools. It's well, for me anyway, it's a completely different way of thinking about it. So as I mentioned at the start, and if there are a few people who weren't here at the beginning of the presentation, you'll see that over on the right-hand side of the box. On your browser, there's a question box on the right-hand side of the panel on your screen, and when you click that, you'll be able to type your questions in, which will come through to us, and we can then ask them to Frank as well. So please, if there are any now that you'd like to send through, please do. I do have a couple here that have come through already, and if I could just put these to you, Frank. First off, this is one that's been put through. Would you say that using 3D printing reduces incidence of human error in the production process?
Well, at least it is a potential to reduce the human error, and I would not really only limit it to human errors. I would prefer to talk about efficiency, and I have mentioned the possibility to reduce drawings, for example. Now, this is something I've not been, because of timing, I've not been able to mention during the BMW example, but one of the major reasons to adapt additive manufacturing for jigs and fixtures at BMW was actually to reduce the need to walk up and down between design office and manufacturing in order to make sure that all these fixtures are assembled in the right way. So there was a need for a lot of communication in order to avoid mistakes. And yes, this is something which can easily be reduced in using additive manufacturing. Why? Well, because I can reduce the number of single components which have to be assembled.
Okay. I do have another one here as well, if you wouldn't mind. I'm just going to pop these questions through to you. But this is the second one that's come through. Could you argue that while the material development side of 3D printing is ahead of the hardware in terms of producing suitable end-use parts, or would you say that the machinery is up to speed already?
Well, let me put it that way. There is a very simple and easy answer, which is yes. The slightly more complex answer is, of course, that it really depends on what these parts are used for. And if we are talking about the famous airplane wing, I would say definitely both materials and technologies are not there yet, by far. But if we talk about, let me say, level B or C components, I would say that yes, easily it is feasible. Why am I saying this? Well, because it's currently done. There are people which are actually manufacturing parts using thermoplastic materials, and we have seen a very quick example of Emma on the right side, where we talk about prosthetics, exoprosthetics. This is something which is currently manufactured. So I would say in that specific case, yes, both material and technology are up to speed. So it really depends on the application, and it depends especially on the requirements of the parts.
Okay, I do have two more here. So an industry like automotive, for example, it's notoriously conservative. How well has 3D printing been received by automotive customers? And would you say that it's been easier to penetrate other markets such as consumer electronics?
Well, if we would have webcam, then you would see me smile a little bit, because who says that automotive industry is conservative? No, I don't know if automotive industry is conservative. It's demanding. The expectations are very high. Conservative, I don't know. And the reason why I'm saying this is that in the past 25 years, it was actually more the automotive industry adapting the new technologies earlier than others. Earlier than others because they have a high demand, high expectation in technologies and not so much in cost. If we talk about the electronics industry, the complexity of electronics is more in the electronics itself. So that's where I see the real conservatism. So yes, it was more the automotive industry adopting the new technologies by experience in the past. And yes, it is really coming up strongly also in other industries, including, of course, electronics, but as mentioned before, even medical and prosthetics and architecture and fashion and many other areas which are picking up very quickly now.
Okay, it looks we've actually just got a few more that have come through, Frank, if you don't mind. It says that people are jumping on board now. Just the first one, actually, I'll just ask the first one that came through. Someone did want to know, with some of these processes that you've spoken about today, are there any videos that you have available that we can send out afterwards as well?
Yes, there are videos not only from Stratasys, but well, I would say the internet, especially YouTube, is full of videos about the technologies. And we talk about first the FDM technology, fused deposition modeling, and this is something which probably is pretty much known because even I would say a wide range of the entry-level printers are using that technology as well. And the other technology is the polyjet technology, where there should be videos as well. And I assume that there are even videos on the Stratasys webpage, but I would have to verify.
Okay, thank you. Now we have one here looking at the injection molding, and particularly looking at the steel industry, or using it in steel. So this person said we've had a couple of cores printed in steel for injection molding, but the issue was surface finish, almost a very coarse sparked finish. What is the best resolution available using steel?
Well, first of all, we don't use steel in our technology, so we're just limited to thermoplastic materials and to photopolymers. And talking about the injection molding application I've presented, this is really printing the mold in photopolymer with a resolution of about 16 microns of layer thickness. So you could expect a very smooth surface finish there as well. But please, let me point out that if I'm talking about injection molding, this is not the try to compete with the metal injection molds for a higher amount of shots. It's more talking about a very early adoption of injection molding in your product development cycle. So it's more competing with silicon molds and not so much with metal molds. So in reality, these plastic molds is more used where the silicon molds cannot provide the desired result anymore. For example, with glass-filled materials, which is something you cannot use in silicon molds, but you can easily use it in plastic molds.
Okay. And again, on injection molding, another question has come through. Can the injection molding process produce soft tooling?
I'm not sure if I understood the question.
Yeah, we might need to. We might need some more clarification of that. If the person who's sent that question through, if you can be a little bit more specific what you're talking about in regards to, was it in regards to soft tooling? Is there something else you'd like to know more about that, Frank, that we might be able to ask?
But I mean, what I've already said, that yes, we are trying to replace some of the soft tooling applications, if this is the meaning of the question. So yes, we are really aiming on these soft tools, but not in order to provide models for soft tools. This is something which is already done, I would say, since 15 years, but really to replace these soft tools, to skip that step of the soft tools. Okay. If this is the question.
We'll have to see if we get something else coming on through that. And just a final question that I have here for now, unless a couple more come through, all this is there, but what do you feel the biggest barrier to manufacturers is to upscale the use of additive manufactured parts and components from thousands to more significant industrial quantities?
Throughput. Okay, let me expand a little bit.
Straightforward.
Just simply, the currently available technologies, and this is not limited to Stratasys, are still, number one, too slow, and number two, too expensive to justify the millions of parts. So these additive manufacturing technologies currently are more limited to the cases where I'm getting in trouble with my current manufacturing methods, where, for example, it does not make sense to make an injection molding tool for 1,000 parts, or where it might not make sense to do the programming effort and the fixturing effort for milling a high complexity, free-form shape metal part. So it is to be considered, at least in our opinion, as an addition to the current manufacturing and not so much replacing any manufacturing, at least not for the next X years. And don't ask me what X means here.
Fair enough, I won't put you on the spot like that. So I think that's all of the questions that we have for this afternoon. Yeah, that's it. I'm just checking confirmation. There's no more questions at the moment, so I might wrap that up there. That'll wrap up our webinar for today. I would like to thank everyone for joining us today. Following this, we'll shortly email you out a copy of the webinar, a recording of the webinar. So please feel free to share this with your colleagues, and we'll provide you with contact details in the email as well. So please do get in touch if you'd like any further information from either the manufacturer or from Stratasys as well. So I'd just like to say to everyone, thank you again, and see you next time.
Thanks for listening to everybody from my side as well.